I'm excited to introduce our next speaker, Alvaro Carbonero from University of Waterloo, who's going to be talking to us about the heroes of digraphs, coloring digraphs with forbidden induced subgraphs. So take it away.
Yeah, thank you everyone for coming to this presentation. I will present to you what I have been working on for the past year or two. I think it's a very exciting subject. I hope that you come out of the talk also thinking the same thing. And yeah, we will have the presentation split into 6 parts. We're going to start by just having some definitions so we know what we're talking about. We're going to play around with the definitions just to see how they feel and whether they make sense. And then we're going to get into the way in which the field has been split into 2 parts, the way in which it has been organized, which is by 2 big conjectures that we will examine, and we will focus on one of them, which is the conjecture on heroes. We will talk about the progress on that conjecture. And then the part that I am very excited about is I'm going to show you some of the new results that I have obtained in collaboration with my advisor, Sophie Spirkl, and 2 other students, Benjamin Moore and Hidde Koerts. And lastly, we end the presentation by going over many open questions that I have and which they keep me up at night. So maybe by the end of the presentation, they will keep you up at night too. We'll see. So let's start by just having some definitions. Proper K coloring is an assignment of K colors to the vertices such that no edge is monochromatic. It's one of the most basic definitions we see in graph theory, maybe even in the first week of Graph Theory 101. We simply assign colors to the vertices such that in the end, every edge is not monochromatic. So for example, this would not be a coloring or a proper coloring because we assigned red to both ends of an edge. And we can follow this definition by creating the chromatic number. So the chromatic number of a graph G is the minimum number K such that G has a K coloring. The way in which I like to think of the chromatic number is as a measure of complexity, how complicated the graph is, because it measures the minimum number of colors we need to create this operation or this property. So it's measuring how simple, in my opinion, how simple the graph is. Let's see an example of a coloring. In here, we have assigned red to left and right, green to top and bottom, and blue to the middle. And as you can see, no edge is monochromatic. And worth noting is that the monochromatic number, the chromatic number is at least 3 because we have a triangle. So we cannot assign colors to the vertices with less than 3 colors, because then a triangle would have, there would be some triangle that has only 2 colors, and that would create an edge with both ends of the same color, which contradicts the definition. So in fact, this has chromatic number 3, since here we have a 3 coloring. One other way to think of this coloring is as a way to split the vertices such that each color class is a stable set or an independent set. Notice that the red edges have no edge in between, and the green edges have no edge in between. That's by the definition. So we can think of colorings as splitting the set into stable sets. And that's what motivates the next definition, which is dicolorings. So Neumann-Lara in 1982 introduced this definition of colorings, but for digraphs. So a proper K dicoloring is an assignment of K colors to the vertices such that no color has a directed cycle. So the key difference here is that an edge may have both ends of the same color, but each color class cannot create a cycle. So let's see an example of that here. As you can notice here, the vertices outside create a cycle. So it would not be okay, or it would not follow the definition for us to give all of these vertices the same color, because if we give them all the same color, then that would be a monochromatic cycle, and that's not allowed. So we are asking then for a way to split the vertices such that each part has no cycles. In normal colorings, it was splitting the vertex set such that each part has no edges. Now it's splitting the vertex set such that each part has no cycles. And in the same way, we can define the dichromatic number, which is the minimum number of K such that D has a K dicoloring. And let's see an example of that. Here we have a K dicoloring. As you can see, the red edges are P3, so it doesn't even have a cycle in the underlying undirected graph. So of course, it is going to be acyclic. And the same for the blue ones. So this has dichromatic number at most 2. And we can't color with just one color because we have a cycle. The cycle on the outside is there, so we need at least 2 colors. Otherwise, that cycle would be monochromatic. So the dichromatic number is equal to 2. Before going to the next slide, let me just point out that this edge right here has both ends in both directions. And the way in which that we can interpret that is as a cycle on 2 vertices. So we cannot color both sides of the same color because that would be a monochromatic cycle on 2 vertices. So one way to think of a coloring, a proper coloring, the one that we all know, is as a dicoloring where every edge goes in both directions. If we think of edges in normal undirected graphs as a digraph where every edge goes in both directions, then colorings and dicolorings are the exact same thing. So K dicolorings are in some way a generalization of a coloring. It's just that now we can only go in one direction when making the cycle for every edge. And that leads me to the next point that I'm going to make, which is that in our context, we will only see orientations. That is, every edge has at most one direction. Even though we can see how they relate, colorings and decolorings relate through edges with both directions, it's very interesting when we only see one direction, when we only see orientations. And we will see how that's really interesting in a second. So now that we have definitions out of the way, let me start by asking you a simple question. Is it even possible to have the chromatic number equal to 3 or more than 3? I think it's good that once we make a definition, we make sure it makes sense, because if every single digraph had the chromatic number 1 or 2, then this definition would not be interesting. So let's try to think of a digraph that has the chromatic number 3. It's very simple to get one with 2, you know, it's just a cycle. Any cycle will work. But the chromatic number 3 is actually not that simple. It's of course possible, as we will see in a second, but it's not that easy to get as one would think. With normal chromatic number, any clique on K vertices, any clique will get arbitrarily high chromatic number. So for example, this clique has chromatic number 4. But when it comes to dichromatic number, it's not immediately obvious what's the answer. And that is, even though there is an answer, we can put something here, it is, I think, very interesting that it's not that easy. We need to put more work to get high dichromatic number. But now that we have said that, let's see how we can get it. For that, we are going to define a tool to allow us to construct bigger digraphs. It's going to be the notation of delta DEF. And that's simply a way to denote the digraph where we have a copy of D, a copy of E, and a copy of F, and all of the edges go in a way that make a triangle. So that's what we denote by delta of D, E, F. And when one of these digraphs is a transitive tournament, which is an orientation of a clique with no cycles, so if, for example, this one is a transitive tournament on K vertices, we simply write K as opposed to TTK because it's just a way to simplify notation to not make it too crowded. All right, so how can we get arbitrarily high dichromatic number? We do this very simple construction first found by this group of 8 people. We will see them again later. They are a very important group. Maybe you recognize some of the names. So the first iteration of our construction is just a single vertex. So the first member of the sequence is just a single vertex. So having defined dn, we define dn plus 1 by adding one vertex, and then we add a copy of dn, another one, and we make them into a directed cycle. So exactly what it says here. And this construction is actually going to have very high dichromatic number. Indeed, it has arbitrarily high. We have this lemma that for every n, the nth iteration needs n colors. It's very simple to prove. Let's go ahead and do that just to get used to these definitions. So the case for n is equal to 1 is very simple, and we proceed by induction from that. Let's assume that the n needs n colors. So now when we are coloring dn plus 1, we consider this graph. Oop, that should be dn. So let's go by contradiction. Let's say that this digraph doesn't need n plus 1 colors. Let's say that it needs n. So that means that there is a coloring of this with just n colors. So this vertex receives some color. Let's say it receives the color green, but dn needs n colors too. So there exists here a vertex that also needs green, and similarly on the other copy, another vertex that also needs green, but that is a monochromatic triangle. So indeed, we need n plus 1. Very simple proof. And actually, by assigning always this vertex a new color, this is tight. We can get equality. So there you go. One way to get arbitrarily high dichromatic number. But let's go beyond this. I think one of my favorite theorems of graph theory is this result by Erdős in 1959, famously by using the probabilistic method, proved that for every number c and g, there exists a graph g. In here, we are talking about undirected graphs, so a normal graph g, such that the chromatic number of g is at least c, and the girth of g is more than g, where, by the way, girth is the smallest number of edges in a cycle. So of all the cycles in G, we gather the smallest one by in relation to the edges, the number of edges, or number of vertices if you prefer. So notice, for example, that girth of G more than 2 already implies that the clique number is at most 2. And this is the case because a single triangle already implies girth 3, girth 2. So I think I confused myself, but the existence of triangles would contradict the girth of more than 2. So that's why this is a very interesting parameter, because it's kind of measuring how small the cycles in the graph are. And given that chromatic number relates to edges and being able to assign colors such that no edge is monochromatic, I think it makes sense to guess that to have high chromatic number, you need a lot of edges in your graph. What Erdős proved is that that's not true. You can have arbitrarily high girth and arbitrarily high chromatic number, and at the same time. So the chromatic number is indeed interesting, it's complicated, it's hard to bound. What I think is also surprising, very surprising, is that the same is true for the dichromatic number. And in here, the girth of a directed graph is the girth of the underlying undirected graph. So as if the same is just the digraph again, but now every edge has no direction. We go back to a normal graph. So indeed, as with the chromatic number, the dichromatic number is very complicated, is hard to bound. Just a special note that I like to point out, Hydrogen and Mohar proved this result probabilistically, and like the same, following a similar technique to what Erdos did. And Alon in 2020 found a constructive proof. So I think that's pretty impressive. All right, but let's go to the next slide. So now we're going to talk about the two big conjectures, because these results are just saying, okay, the dichromatic number is interesting, but what can we do with it? We're going to split the field into two conjectures, and for them, we need some definitions. In particular, the most important one that we need is for induced subgraphs. So a digraph H is an induced subgraph of G if we can delete vertices from G and end up with H. So let's say, for example, we have a graph G. H is an induced subgraph if H exists within G, but with no alterations. We don't have to delete or add any edges. It just is there. And consequently, we say that a graph G is H-free if H is nowhere to be found, if H is not an induced subgraph of G. And lastly, just to make our lives a little simpler with notation, we're going to define H1 arrow H2 as simply the digraph where we get a copy of H1, a copy of H2, and we put all of the edges from looking in the same direction, so from H1 to H2. And with this, we have what we need. So let me ask you a question. We're going to ask questions all the way until we get to the conjectures. The question is, what causes tournaments to have high dichromatic number? Our construction that we saw before, the one with the N, this one was really interesting because it allowed us a very easy way to get dichromatic number. You know, the proof is what, half a paragraph? So that's very simple. So why is that the case? Why can we get high dichromatic number in tournaments? There are many ways to answer this question through non-induced subgraphs ways. So let me make the question a little tighter. Does having high dichromatic number imply the existence of certain induced subgraphs, where in here, I mean in tournaments? So in the context of tournaments, does there exist digraphs such that if you have a tournament with high dichromatic number, then you are forced to have these smaller substructures? And that's what inspires the definition of heroes. So let's see be a class of digraphs, for example, tournaments, which, by the way, maybe didn't mention this, is oriented cliques or oriented complete graphs. A digraph H is a hero in the class of digraph C if there exists an integer C such that H-free digraphs of the class have bounded dichromatic number. So we are talking about a class of digraphs, and we are saying that H is a hero in that class of digraphs whenever H-free digraphs have bounded dichromatic number, and that bound is given by the number small c. In this talk, basically in theory, C could be whatever you want. But in this talk, we will restrict ourselves to the case where C is the set or the class of F-free digraphs for some digraph F. So what this results in is that H is a hero in F-free digraphs if H, F-free digraphs cannot have arbitrarily large dichromatic number, or equivalently, they have bounded dichromatic number where the bound is given by little c. All right. So now that we have these definitions, we can talk about the question again. What are the heroes of tournaments? what structures need to be present in every tournament with high dichromatic number. And I think I should have written here heroes in tournaments, not of tournaments. So let's go over some observations. Probably the simplest one is, or one of the simplest ones, is that transitive tournaments are heroes. One result that we see, we can learn about in Graph Theory 101 is that if T is a tournament and is TTK free, then T has at most 2 to the k minus 1 vertices. It's usually thought of as the contrapositive. If T has more than this number of vertices, then we can find a transitive tournament on this number of vertices. In our context, though, it's better to put the contrapositive. So that implies that if T is TTK free, then T has a bounded number of vertices. And then we can get the worst coloring of all, which is every vertex gets the same gets a different color. And that leads us to the conclusion that the chromatic number is at most 2 to the k minus 1. So this is our little c. And indeed, transitive tournaments are heroes. Probably a simpler observation than this is that directed triangles are also heroes, because if your tournament is not transitive, so if there is a cycle in your tournament, then T contains the directed triangle. So the contrapositive is that if T is directed triangle free, then T is the transitive tournament. So the dichromatic number of T is literally 1. We need one color to color the whole thing because there is no cycles. So we don't have to worry about a monochromatic cycle. These are the easy cases, though. Like they are the easy ones that we can get after thinking about the problem for an hour or so. What about other cases? What are the other heroes? And here is where the people of the first result that I showed you come into place again. These 8 researchers found a full characterization of heroes. That is, they proved that H is a hero in tournaments if and only if one of these holds. And before going into what those are, let me explain how you should think about them. We're going to see a building block, and then we will see ways to create bigger heroes. So we're going to decompose heroes into building blocks. In the case of tournaments, it's simple. The building block that we need, the only one, is K1. So K1 is a hero, which should not be surprising because this is TT1. And from K1, we can make bigger heroes through 2 operations. The first one is this one. We can make one hero be looking at another one, or what I would say is concatenate them. We can concatenate one hero with another one to make a bigger hero. And we can make use of the delta operation. And we get that we can construct bigger heroes by using a transitive tournament and another smaller hero. So these operations create heroes. And what these people proved is that these are the only ways to create heroes. All heroes can be deconstructed through these methods. So let's get a taste of the proof, because it's a 25-page proof. We're not going to go over the whole proof, but let's prove one small part of it. Let's prove the part that strongly connected heroes need to have this form of delta 1 pk, where p and k are heroes. If you notice, the tournament result, the one from the last slide, proves that one of these, in addition, also needs to be a transitive tournament. So we're going to prove this result. And I think if you have never done research in the area, it might sound really intimidating to prove this, but it's actually not that hard. We will use that construction that we saw at the beginning to do it. So just as a reminder, this construction has one vertex and two copies of the previous iterations. We make a triangle, and then we have the next iteration. That's the n plus 1. So how can we do it? Well, first of all, we will go by direct, we will have a direct proof. So let's assume that H is a hero, and it's also strongly connected. Since H is a hero, in tournaments, we have that there exists an integer C such that H free tournaments have the chromatic number at most C. That's what the hero means. So we have that. All right, but by the lemma of the dichromatic number of this construction, the dichromatic number of DC plus 1 is equal to C plus 1. And these guys are tournaments. So H exists in DC plus 1. All right? And here is where we do a little trick. We are going to notice that this construction is actually, it contains itself, oh, that's an epsilon, sorry. The next one contains the previous one. So there exists a smallest n such that H is in Dn. And now we are so close to the proof. We have one more argument left. Let's look at Dn. Here we have Dn minus 1. Here we have Dn minus 1. By the definition of n, H is not here. H cannot be here because otherwise n would have been n minus 1. So H is also not here. But where else can it be? H is strongly connected. So H cannot be distributed among these two classes because that's not strongly connected. It has all edges in one direction, so we can, so it's not strongly connected. And furthermore, for the same reason, H cannot be here because again, this would imply that it's not strongly connected. And finally, it cannot be here, but we have run out of options. The only other possible way in which H is here is if H is in the entire thing. It's distributed on the free parts. That gives that H has the form 1 pk. And since all the induced subgraphs of a hero are also heroes, I'm not going to prove that one, but just trust me on that one. Then these two are heroes too. And there you go. A very nice proof, and hopefully it'll get you a little more used to the idea of heroes. And now we're going to finish. So now this is a study of the case where C is tournaments. What about the other ones? We are going to study the other cases by following the way in which Abulker, Charbit, and Naseras organized the field. In particular, we will use many observations and then gather a conclusion that will lead us to the two conjectures. The first observation is that tournaments are actually 2k1 free digraphs. So remember when I said that the classes C that we're going to consider are actually F free digraphs? Well, this is, so tournaments are the case where F is just simply 2 vertices. All right. The next observation is, let me skip this one. If you can read it on your own time, like but I'm not gonna cover it because it's a little complicated. And what we need to gather from it is the third bullet point, which is that if F contains two non-adjacent vertices, and H is a hero in F3 digraphs, then H is a hero in tournaments too. So if F contains a single pair of non-adjacent vertices, no matter how big F is, and H is a hero in F3 digraphs, then H is also a hero in the case where F is just two isolated vertices, so it's a hero in tournaments. If so that's what these steps allows us to conclude, and it's really important because we know how the heroes in tournaments look. That means we have we may not know the heroes of F, but we know how they must look, the structure of them. We can construct them through a couple of operations that we saw in the theorem before. So that's great. We have limited the pool of heroes to a set that we know how to define. The next one is that every digraph is a hero in K2 free digraphs, because if we forbid K2 as an induced subgraph, K2 is an edge. So what's left? K2 free digraphs are just stable sets. They have the chromatic number 1. So let's just not think about this case. Lastly, and the most complicated observation, is that we may assume F is an oriented forest. That's a little bit of a big one, so let me very quickly prove it. We're going to use the theorem that we saw at the beginning of Harajunjan and Mohar. They proved that for every number C and G, there exists a digraph D with the chromatic number more than C and girth more than G. All right, how can we do that? We're going to prove this result, which will imply the observation. We're going to prove that if H, F free digraphs have bounded the chromatic number, then one of them is an oriented forest. So let's do it. We're going to go by contradiction. We're going to assume that this statement is true, and then gather a contradiction. So H and F free digraphs have bounded the chromatic number. Let's say it's C. So if we are H and F free, then the dichromatic number is at most C. And none of them are an oriented forest. So that means that they have a girth. So let's set G equal to the maximum of the girths, the girth of H and the girth of F. What do we get from this? We get that from the theorem, there exists a digraph D with girth more than G and dichromatic number more than C. But we are in trouble because this implies that D is H, F free. And that implies that the dichromatic number is at most C, but that contradicts the definition of D. So contradiction, one of them needs to be an oriented forest. And if you wonder where the proof would go wrong, it's because we define, and for this theorem to work, we define the girth of forest to be infinity. So this would not make sense. That's why the proof would not work if we have this assumption that one of them is an oriented forest. And that's why, by the way, we always use F, because F is for forest. All right. So these observations can be summed up in this one. Assume that F is not an edge, and assume that F is an oriented forest. Then if H is a hero in F3 digraphs, then H is a hero in tournaments. Great. Awesome. But there is one more thing. I think one question that could follow up from this is the converse true? What about the converse? The answer is a little simple. It's no. Abulker, Charbit, and Nasserars, in their quest to divide the field into two conjectures, they proved this theorem, which is that assume H is a hero in F3 digraphs if the underlying undirected graph F contains a P4, so a path on 4 vertices, then H is a transitive tournament. So the only heroes that work when the underlying undirected graph of F contains a P4 are transitive tournaments. And the proof is actually very simple. I want to show it because I love constructions. I think they are just pretty to look at, and they create a lot of understanding of the subject. This construction is going to be very simple. We're going to abuse the notation of delta here by putting 4 elements. It simply means that the previous iteration, we're going to make 4 copies of it. And now we're going to make a directed cycle, this time with the 4 copies. And then we repeat. We put 4 copies of the previous iteration, and we put edges in a directed cycle. And this time, the dichromatic number is actually more than just n. It's, I think, 2n, or even more than that. All right, so we have that. And why is this important, though? Why is this construction important? The first thing is that all tournaments in the construction are transitive. And that's really important. If you can think about it, but it's not super hard to see that, yeah, all tournaments are transitive. And that means that, let me before saying what that means, let me give the next observation. The underlying undirected graph is P4 free. This one is a little easier to notice because where could a P4 be? It cannot be between 2 copies, because then it would not be P4. It would not be induced. It cannot be between 3 of them again, because it wouldn't be induced. And it cannot be between 4 of them, because it wouldn't be induced again. So it is P4 free by induction. And that means that heroes when F contains a P4 need to be heroes. Wait, let me think about what I just said. That means that when your F contains a P4, this class of digraphs will be contained in your class C. And since these guys only have tournaments, then the heroes need to only be tournaments. Because if you have a hero that is not a tournament, a transitive tournament, then this would be a counterexample to your conjecture of heroes that are not transitive tournaments. And so again, summarizing, we have proven this theorem, which is that if the underlying undirected graph F contains P4, then H is a transitive tournament. What the conjectures are, which we are about 1 slide away from seeing them, is that everything else works. They conjectured that every other statement works. That is, they conjecture that if F is an oriented forest and H is a transitive tournament, again, because this is the case that, so this is a conjecture, this is a construction for just transitive tournaments. They conjecture that they are going to work in other cases. So if F is an oriented forest and H is a transitive tournament, then H is a hero in F digraphs. This is super open, very hard to. The best case known is orientations of P4, which was proven late last year. It's a very cool proof, and I could do an entire presentation on this conjecture, but that's not the subject for presentation. Let me just do one more note. This can be seen as the directed Giarfas Sumner conjecture for the ones who like structural graph theory. I'm not going to define the Giarfas Sumner conjecture because that's going to take some time. But yeah, it's just a way to compare this result to the undirected case. It's really hard, just like the Giarfas Sumner conjecture. The other conjecture that we see is this one, which is if F is the disjoint union of oriented stars, and H is a hero in tournaments, then H is a hero in F-ray digraphs. And you might wonder, why disjoint union of oriented stars? That's because this is exactly P4 free digraphs, or oriented forests that are P4 free. So they conjecture that when P4 is absent, everything still works. And as we can see here, that conjecture is false. And this is what we are going to talk about in the rest of the presentation. We're going to talk about the progress in the conjecture. Let's start with the positive results. So this paper called Color Intense Digraphs, written by Hidde Koerts, Lee, Neumann, and Thomas A., proves that the conjecture is true when F is RK1. So they prove that this, you might notice that this is the exact same characterization we use for heroes. They are saying the heroes of F-ray digraphs when F is RK1, and that means, by the way, R copies of K1. In this case, that's just R vertices in a stable set. They prove that the heroes in that class of digraphs are exactly the same heroes as tournament heroes, which is really cool. I think really impressive. It takes them like 20 pages, a hard result indeed. And another positive result is that the conjecture is also true when F is P3, the directed path on free vertices, in particular, this orientation, all forward. This was proven by Abulkar, Albion, and Charbit. And it's really cool. Again, the conjecture works for P3 free digraphs. And in the same paper, these people proved this one, that the conjecture, like they partially proved the conjecture for complete multipartite digraphs. So complete multipartite digraphs are simply a digraph when you can split the vertex set into parts, and then every single edge possible is between the other ones, all the other classes. And you can characterize these digraphs as being K1 plus K2 free. So they proved this. They proved that similar to the tournament result, we can have as a building block the single vertex. We can then concatenate two digraphs, and very, very important in here, you can, to construct bigger, strongly connected digraphs, we can use this operation. Instead of in the tournament result, we get 1, M, H1, they have that M has to be equal to 1. So when M is equal to 1, this works. And I think you might wonder, well, is maybe like a better proof or a stronger proof might get more than this, but they proved that that's not the case because they found a counterexample to the conjecture. In particular, they proved this. If C is the cyclic triangle and F contains a copy of K1 plus K2, then these guys are not heroes. 1, 2, C, 1, C, 2, 1, 2, 3, and 1, 3, 2. So we get that our heroes cannot contain these guys because otherwise that would be a contradiction to this theorem. And we get that we can construct heroes using these operations. So what's left? What's left to get a full characterization of the heroes of K1 plus K2 free digraphs of complete multipartite graphs? The only other open case is 1, 2, 2. This does not contain any of this, and this cannot be constructed by all of the other operations. And it's the only case that has these properties. If 1, 2, 2 is a hero, then the characterization can be completed by simply adding it as a built-in block, and then we're good. If it is not, then the current statement is already a full characterization. By the way, this case can be related to ordered graphs and chi-boundedness in ordered graphs. But that's another subject. We're not going to talk about that. It's surprisingly hard. It's really fun, though. We tried to prove it or disprove it for a long time, my group and I, and it's really hard. Still open though, still open. And I think what the way in which I'm going to organize our results is as quantifying how false is the conjecture. The conjecture was made 2 years ago. We've known it's false for a year already. But now it's fun to see how false it is, what is true and what is not. So notice that the conjecture, it was proven for RK1, it was disproven for K1 plus K2. And what's special about K1 plus K2 is that K1 plus K2 is the smallest disconnected case with an edge. So if you get an oriented forest that is disconnected and that contains an edge, this will be the smallest one. So for the smallest one with an edge, the conjecture already fails. And also, yeah, so also the conjecture is false for forests with an oriented edge that are disconnected. So I think it's reasonable to ask these two questions, that maybe the conjecture is true for oriented stars. That is, let's remove this part of this joint union. Maybe the conjecture then is true. And the second question is, maybe tournament heroes are just too strong. They are just too big. So what heroes do work? Because it's not like one or the other. It's not like everyone works or only transitive tournaments. There is an in-between. So where is that in-between? And here is where we get to our new results. We're going to go first for the second question. So let me start by asking this very simple question. If H is a hero in every digraphs, and is it also a hero in K1 plus every digraph? So can we add a vertex to F? The answer is no, very simply because 1, 2, 3 is a hero in K2 because everything is a hero in K2, but it's not a hero in K1 plus K2 as we saw before. So the answer is no, but we can make it work a little bit as I will explain in a second. That's the kind of the motivation of the work that my group did. We're going to define this. F cooperates if we can use these tools to construct bigger heroes. And again, this is the same construction that we saw in the case of complete multi-part digraphs. What that paper proved is that K1 plus K2 cooperates. So now to like not have to repeat this construction a bunch of times, we gave it a name. If these construction rules work, we say that the graph cooperates. And we are going to use this definition, K-local. A digraph D is K-local if the dichromatic number of the out neighborhood of every vertex is has dichromatic number at most K. You don't have to understand this definition. It was first proposed by Harold Junjun, Lee, Neumann, and Thomas A. in a paper. And I say this because this is a little complicated, and it might be the first time you guys are seeing this theory. So, just just try to get the essence out of this, which I will try to emphasize. What we define, we create a new definition, and it's that F is localized, roughly speaking. We're not going to go into formality. If 1,1H is a hero in K-local, K1 plus every digraphs. So we are giving ourselves the aid of also adding to the constrictions that we are working with K-local digraphs. And if you want to know what H and K and F are in this context, here is what they should be. But again, we're not going to get boiled down on details. It's just a way to exemplify what we're going for. This definition is heavily inspired in the proof of the RK1 result, that heroes in tournaments are exactly the same as heroes in RK1 free digraphs. So I just want to give them credit because we did borrow some of their ideas a lot. What we proved is this: if let F be localized and co-localized, which again I didn't define co-localized formally. Don't worry. It's just for now, just take it as a word. If F cooperates, then RK1 plus F cooperates. That means if we can use that set of construction rules to get bigger heroes for F, we can also do it for RK1 plus F. Our proof technique uses the again the paper that proves the conjecture works for RK1. That we use the proof technique as in a more general context, and we get this result, and we use it to prove what's I think very exciting. It's this one. For every R at least one, H is a hero in RK1 plus P3 free digraphs if we use these tools to construct. That is, this guy cooperates for every R. So we can keep adding vertices to P3, and these heroes will keep working. So I think it's really cool. And here, as by the way, our collaborators, Moore, Koerts, and Spirkl, we are writing the paper it's going to be on the archive in a month, maybe. My thesis has the case of K2, but we managed to improve it. My thesis should be up in like 2 weeks. Really excited about that. All right, so now let's go on to the other question. So remember, we pondered about the idea of whether maybe if we were to remove the condition of being disconnected, the conjecture would work. So maybe the conjecture works for oriented stars. And what we give is that that's not true. Again, a result by the same group. We proved that if F is an oriented star of degree at least 5, then H is a tournament in every digraphs, if and only if H is a transitive tournament. We get a full characterization of heroes in this class of digraphs, and it's that nothing works with the exception of transitive tournaments. Not even the directed triangle. Nothing works, just transitive tournaments. And we also get the slightly smaller result that when it comes to degree 4, it's either transitive tournaments or heroes of this form. This is still an open question. I honestly wouldn't know if this works, but it is one of those two. And with this, we lead to the questions that keep me up at night. So it's a couple of questions, and then we finish the presentation. The first question is, what other digraphs cooperate? Because we know P3 so far is the biggest digraph that we know cooperates, with the exception of RK1. So it would be good to find more that cooperate. The second is, what other digraphs are localized and colocalized? Because if we get one that is colocalized and localized and cooperates, then we can use our result to keep adding vertices and still get that it cooperates, which would be cool because they would use our result. And the third one is really big to me. Do we actually need the assumption that F is localized and colocalized? Or do we always get that we can just keep adding vertices for free? I don't know, big question. The next one is, we have been adding vertices to F, RK1, but can we add more than that? Can we add edges instead? For reasons that I don't have time to explain, this is way harder than adding a single vertex. Like I think it's obvious that it's harder, but it's actually way harder. So I don't know, that would be interesting to see. Is the conjecture true for oriented stars of degree at most 3? We proved that degree 5 doesn't work. Degree 4, it's most doesn't work, but maybe a little bit works. So what about 3? We don't know. Very few structures have been proven to work. So still open question. And lastly, is this other open case possible or not? Maybe one of them needs to be 1. Maybe both of them can be more than 1. Open question. I honestly, if you ask me, I have no idea what's the answer to any of these questions. They are really, really open and really hard, and I think really cool. And with that, I finish my presentation. If any of you have any questions, I would welcome them.
Awesome. Thank you. Any questions for Alvaro? My main question is silly, which is, why are they called heroes?
That's a good question. I don't know. The paper that characterizes heroes is a paper that gives them the name
Yeah.
So I don't know. I like the name though. It allows me to have very silly titles.
Yeah.
Yeah, I hope the field sticks to that name. It's really cool.
Any more serious questions? Yeah, Enrique.
Yeah, so I have a question. So earlier in the presentation, there was a slide where you talked about how there was a class of graphs that have arbitrarily high dichromatic number. And I don't know if you said anything about uniqueness. Are there other graphs that also have arbitrarily high dichromatic number?
Just take a random check.
Do you mean this slide where we saw the?
I think it was previous to that.
Do you mean these ones?
Yeah.
So that's actually that would be a good guess that maybe these are the only tournaments with high dichromatic number, but they aren't. They are a simple one, but there are other more complicated ones. For example, the paper that proves the Hidde tournament characterization also defines this class called RK mountains, which are really hard to understand, in my opinion. Their definition is like a quarter of a page of very dense inductive things. So the answer is no. There are other ways to construct high dichromatic number in tournaments. So yeah, this is not unique.
Thank you.
Furthermore, those have really low chromatic number. If you just take a random tournament, it'll have dichromatic number n over log. Whereas those have chromatic number like log number of vertices. So these random tournaments have crazy high chromatic number compared to the other vertices.
Okay, awesome. Well, let's thank our speaker one more time.
Thanks for the questions.
And congrats on defending.
Thank
Sounds
you.
like.
Yeah, these are the results that are in my thesis.
That's
So